Good afternoon. Welcome to a panel discussion, the last session of the InnovationXLab, where we will tackle as a group one of the big open challenges. We will talk about quantum computing software, architecture, and simulation. And to put this in perspective, when we look back at the digital computing world, thinking about architecture was a issue that was, in a sense, addressed and solved in the late 1940s with von Neumann architecture, which became, until massive parallelism arrived, the standard architecture for computing platforms. And then in the 1950s, higher level programming languages were developed, and that led to compiling technology. And then we had, over the decades, the development of operating systems and other tools that made digital computers as useful as they are today. And in quantum computing, we are probably, to measure it on the digital computing dates, in the late 40s stage. And therefore, the question of software architecture and then what simulations we can do on these systems is a big question for the future of quantum computing. So I'm very pleased to have a distinguished panel of experts who have thought about this and worked in this field here with me. My name is Horst Simon. I'm the Deputy Lab Director for Research at Lawrence Berkeley National Lab. And my history and background is in traditional high-performance computing. I've been working in high-performance computing since the early 80s. And so I'm using the progress that we've made from the megaflops era in the 70s and early 80s to the petaflop to exaflop era that we're currently in. Many orders of magnitude improvement, plus incredible increases in productivity and incredible increases in simulation capabilities as something to compare to quantum computing. So with that, I want to turn this over and ask my fellow panelists to introduce themselves. And so let me first ask Prineha Narang to do her introduction.
Absolutely. Thank you so much for having me here. And it's, of course, a privilege to be with such a distinguished panel. My name is Prineha Narang. I wear two hats. I am on the faculty at Harvard. I've been there for a few years. I also serve as the CTO of Alero Quantum. And today here at the panel, I hope to, putting on either or both hats at times, try and emphasize where the field is going and what the role is of both academia and startups in developing quantum software.
Okay, thank you. So let me ask next, Nathan Wiebe from PNL.
My name's Nathan Wiebe, and I work at Pacific Northwest National as well as the University of Washington in the physics department. And I'm a specialist in quantum algorithms, mostly focusing on algorithms for simulation as well as machine learning. And sort of the, one of the things that I'm really kind of interested in and hope to bring up in this, conversation is identifying what really the killer applications are going to be for quantum computing so that we can get an idea, once we exit this 1940s era that we're in, what really are going to be the major applications and what sorts of quantum computers are we going to need to build in order to realize those applications?
Thank you, Nathan. And then I would like to ask Chris Brown with Zapata Computing to introduce himself.
Thanks a lot. And, it's always a pleasure to join a panel as distinguished as this one. So thanks for inviting myself and Zapata to participate today. My name is Chris Brown. I'm the Director of Quantum Solutions and GM for Asia at Zapata Computing. I've been here about 2 years, and I came from a long history. I thought I'd be at one company. This is my 6th and last, I hope. But I've been working over the years, got a PhD at the University of Texas at Austin and a biochemistry and molecular biology background. And so from my viewpoint of the quantum computing industry, I kind of see it through the lens of all these other fields that I've worked in, including the 20 years I spent in OLED display manufacturing and material science, which is really what brought me here today, because, you know, as somebody who led teams making molecules and feeling the heat and pressure for my senior management to deliver on long timelines, I see quantum computing as, of course, being a pathway finally to accelerating that materials and pharmaceutical drug discovery process. So yeah, I'm happy to be here and look forward to the conversation.
Thank you, Chris. And then I would like to ask Martin Ruttler to introduce himself.
Good. Thank you, Horst. First of all, let me begin by saying it's a pleasure to be in this panel. And generally, it's a great time to be working in quantum computing. It's a very exciting field. My own journey started in 1996. Believe it or not, I attended a course at the University of Karlsruhe on quantum computing. I was instantly hooked about this computational model, which seems so powerful, but which has all these quirks to it. At Microsoft, I work on finding new applications for quantum computer. At the same time, we look into research of the compiler stack. That's a pretty big area. And then also I work on resource estimation. So you want to get an idea of the footprint of a computation even before you run it. So I'm generally intrigued by that model and by the dramatic speed ups you can get for some kinds of problems. Thank you.
Thank you, Martin. So what we'll do first is I have a round of questions, one for each panelist, and we're going in reverse order of the introductions. So my first question is for Martin. And Martin, Microsoft has been a leader in quantum computing for over 20 years. Can you comment from your perspective on Microsoft's approach towards programming a quantum computer?
Thanks for the question. Let me unpack it. So at Microsoft, we develop an end-to-end approach, and I want to unpack that a little bit for you, what it means. So essentially, we want to start with the right type of applications that really have a lot of promise for the quantum computer. And then we want to be able to express those applications in a programming language that's capable of expressing it naturally. So you can actually express your applications at a high level, and you don't have to get worried, have to get bogged down with nitty-gritties of details of the bit level operations. We want to hide that as much as possible from the programmer so that he or she can think about the algorithm that he or she wants to solve rather than the bit level details. And with that comes a programming experience, has dev tools, a rich set of libraries, so that you get a pleasant experience when you program the machine. What happens next is then the compiler takes the program, transforms it internally, and optimizes it for the given target architecture. And then finally, we would have backends. And currently, the main backends we're using are resource estimator backends, simulator backends, the various types of simulators for special purposes. And long-term, of course, the view is to have actual quantum machines being the backend. One of the principles behind our software stack is that we would ideally want to have the code only written once, so you don't have to reinvest and reinvest as the hardware changes. You want to have the same code. You want to write it once and for all, and let the compiler do the job of adapting those things. We're pretty excited about Azure Quantum. So what that is kind of a software stack, a cloud solution that allows you to target quantum machines that our hardware partners provide already today. So those are early hardware providers, and they are in an open ecosystem. The partners include Honeywell, IonQ, QCI, and others on the quantum side. And we have quantum-inspired solutions, which are classical solutions for hard optimization problems, but where quantum mechanical thinking allows us to tackle the problems. So our kind of philosophy is that we want to have impact today. We want to be able to write quantum programs already today and perform resource estimations of these programs today. And then tomorrow you can run the algorithms that you designed on the future quantum hardware.
Chris, you're the chief technologist at Zapata Computing. So what do you think is the greatest need for quantum computing software, and how can we make access for users easier?
Yeah, and that's the key question right there at the end of the sentence, and that's kind of where I started my answer, which is we have to keep it simple and make it as powerful as possible for the customer, and that's one of the challenges I have talking to customers every day, especially if they aren't very experienced with quantum, is to help them get their heads around this challenge, and and all that's happening. As you're trying to explain this, you're trying to help them get their heads around the fact that quantum mechanics is complex, right? If that isn't complex enough, the ecosystem itself is also quite complex, even just for the software piece of the ecosystem. And then the next portion of the conversation typically is to migrate into, guess what? Not just the software is complex because of the compiler and the control layers, and then Zapata's orchestra layer, which is the algorithm layer of the software platform that we've commercialized, but also that, oh, guess what? There are all these different hardware platforms you have to deal with: ion trap, neutral atom, annealing, superconducting, photonic, and that list is likely to grow over the coming years. And then the customer will say, well, which one do you think is going to win? And my answer is almost always probably not one, probably many, and each one with its own unique features. And so helping to communicate that complexity, I think, is extremely difficult today for all of us. And so a key for us is that, our software tools in aggregate, not just Zapata's orchestra software, but all of us together help make this easier for the customer and the community to work together. And that's about to change. I was very excited with IBM's announcement of 1,000 qubits in 2023. Okay, so that's a big step. I can't wait for that to happen. But that adds complexity as well, because now we're no longer messing around with just 5 or 6 noisy qubits, but now we have some logical qubits to play with. And so that's going to require that from a software standpoint, that we continue to develop our platforms and make it easy for the customer to utilize for their use cases and applications. Just a note of congratulations to the DOE though, and that has to be factored into our software conversation. Standing up these 5 quantum information science centers is a huge step forward. I think it's a great step forward, maybe akin to the Moon project here in the United States. But we got to take the next steps and make it easy for enterprises and companies like Zapata to come and work at these centers and help develop these use cases and applications to really grow the industry. And that introduces some complexity, and maybe it requires that we think creatively about how we as a community can make that happen and go fast enough to stay competitive with our competition.
Thank you, Chris. Let me move on to Nathan. So Nathan, you have worked on exploring whether quantum computing can be used to resolve chemical reaction mechanisms, and you have developed algorithms for quantum-based AI. Can you give us a sense how transformative these quantum-based computational approaches are compared to existing approaches based on classical computing?
Wonderful. Yeah, I'd be more than happy to do that. So one of the things that I want to kind of, get out of the way is the speed comparison issue. So taking a look at chemistry, people often end up looking at quantum computing as something that will revolutionize how quickly we're able to do quantum chemistry calculations. But it turns out that issue is a little bit more subtle than it might seem at first glance. When you take a look at some of the classical approximate algorithms that are used to solve problems in this space, many of them actually run in time that's comparable to how long it would take to run a quantum calculation. The thing that the quantum calculation ends up allowing us to do is to do this using far fewer approximations. And so for systems that have properties that defy the classical approximations that we can end up using, such as systems that have very strong electronic correlations in them. Examples of these tend to be problems that involve transition metals or excited states. Those sorts of things, a quantum computer can be truly transformative at, because of the fact that, the approximations that allow fast classical simulation just are no good under those circumstances. And so there's examples of problems in catalysis, as well as other areas, such as batteries and the works that end up often kind of lending themselves to quantum solutions rather than classical solutions. But another thing that's worth bearing in mind is that often we're not actually talking about using a quantum computer as being the only tool to solve these types of problems. The reality is that often what we actually want to do is we want to break up some of these hard problems into parts that are solvable classically and other parts that require a full quantum solution to it. And a lot of the art of building a system for this is going to be integrating the classical algorithms that are currently being used in electronic structure packages, for example, with these quantum solutions as kind of a coprocessor in order to be able to solve the full electronic structure problem. And so for these areas, we've got a truly compelling answer where, you know, quantum computers can provide speedups that are factors of 1 billion for practical problems better, even with the slow gate speeds that we're anticipating for quantum computers, than classical. When it comes to the AI, which is the other question that you answered, that discussion is a lot newer. And so, and a problem is that with quantum simulation, there's direct quantum effects that we're trying to mimic on a quantum computer. So in some ways, the application ends up very, very easily mapping to the hardware that we end up having. And when you have an application that maps to a hardware, even in classical or in quantum, you tend to expect bigger speedups. When it comes to the AI applications for existing problems, we often can end up showing quadratic advantages over the classical algorithms that we have at the moment. However, the same sort of transformative exponential speedups that we end up seeing for some chemistry applications are elusive for AI. However, the thing that I think is potentially really fascinating about this is that for cases where we're trying to learn information about quantum systems themselves, the tools that are being developed in quantum machine learning and artificial intelligence often represent kind of our only tools that we end up having for developing deep understanding for complex quantum states. And so one of the things that I think is going to be quite interesting is understanding the role that quantum AIs might have in understanding quantum systems as well as quantum computers themselves.
Thank you, Nathan. So let me ask Prineha, since you're the founder and CTO of Alero Quantum, a startup company, as well as the faculty of Harvard, so your goal is to lower the barrier to entry into quantum computing for users and businesses. Can you tell us how Alero achieves this lowering the barrier? And how do you go truly cross-platform with the heterogeneous hardwares out there today that we've heard already from Chris?
Fabulous. Okay, so I'll try and answer those questions somewhat sequentially. So our goal really is around being cross-platform. And part of this is recognizing a few different things. One, that knowing which of the platforms there's a zoo of different platforms out there, and not all of them are at that same level of maturity. We expect hardware improvements across each of these, right? Whether it's superconducting, we've heard the various announcements from IBM. Jake Gambetta really led the charge in announcing that in his recent blog post. There have been announcements from folks on the trapped ion side. There have been other announcements from folks in photonics, and of course, various neutral atom platforms that we've just started to hear about more and more. So when we talk about that to folks who want to program hardware, immediately by this point, the answer I get is, whoa, 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 whoa. That's already 5 more things than I ever needed to know about using high performance computing. Of course, this is something that, you know, maybe you'd appreciate. I've used NERSC for decades, and I have never had to know, you know, NERSC in that level of detail that, you know, all the way back from being an undergrad to today, you know, just thinking about, I've seen it once on a tour, and that's about it. And that's the amount I needed to know about it, right? So all those people out there who want to program this hardware, they want to access the power of quantum computing, don't want to know all of this level of detail. They don't want to know about connectivity. They don't want to know about, you know, what is your gate fidelity here and how can it be optimized. Day to day, they can be calibrations and improvements on the hardware that change how you run, say, yesterday versus today, or things around that. So we need abstractions. The challenge with abstractions, of course, is that as soon as you start to introduce some of these abstractions, you lose performance. And that's really where some of the fear comes in, that if I'm losing performance already on hardware that is limited, that's going to be a problem. Or worse yet, if I write something for a certain layer right now, how is that going to be different, say, 2 years down the line when we're at a different point in the roadmap associated with some of the current hardware? So our focus has really been around how do we make sure that things around noise-aware algorithms, noise-aware approaches, noise-aware compiling, in general, noise models, by the way, which are different for these different types of hardware, and how you would treat that is fundamentally different. You know, some of them, maybe a Markovian model is okay. Some where you really need to treat the non-Markovian behavior very, very specifically to roll that into our platform such that all the software engineers who are out there who don't identify as quantum information scientists can actually use the hardware. So that's really where we've been focused. One of the other things that has been extremely important and maybe is something that we'll get a chance to hear about from other panelists as well, is in accessing at the pulse level the hardware and seeing what performance improvements that can give us, or even going beyond performance improvements if it allows us to compute in slightly different ways. So of course, we're used to thinking about qubits and thinking about two-level systems, but that doesn't mean that we can't use and think about, say, qubits, for example. And that's really, access that comes at the pulse level would allow us to, again, implement algorithms that take advantage of those intricacies. The final point I want to make, and this is really around, where I see the interactions between folks who are developing hardware and software approaches and folks who have problems of value. Those problems really span a very large spectrum. There are people who are coming at it from a condensed matter theory or a quantum chemistry standpoint. We heard about that from Nathan a little bit. But there are also people who are coming at it from a very different, now I want to think about this from a finance perspective. I want to think about this from risk analysis. And taking all of those people and getting them to have a coherent conversation is incredibly challenging. So I think that's where I see roles of companies that are represented here today and events like this, where we can really coalesce and say, okay, what are the challenges and how are we all working together as an ecosystem solving these challenges? So.
Thank you, Prineha. So I'd like to move to our next phase, and I have a couple of questions that I will ask all of you. And I like to ask fairly simple questions, but they may have difficult answers. And please don't forget that you're on record and we can look at this in 5 years and see whether your predictions and assumptions are gonna come out correct. So let me ask a very simple question and ask you, what will be the first useful scientific simulation run on a quantum computer that will transcend what can be done on a classical computing system? We've heard some suggestions from Nathan already in terms of chemistry for transition metals, for example, but when will it happen? And so I'm asking you from the, let's say, Department of Energy, high-end computing and simulation community point of view, when will we be able to use a quantum computer to do something that the current crop of excess flop systems that will be installed in the next year can't do?
Yeah, I think there'll be discoveries in predicting correlated condensed matter that have not been possible on even some of the most powerful, classical systems out there. I say that, in contrasting these very, very large exascale systems with quantum computers, I think what's important to remember is you're getting different information, and it's entirely possible to synthesize a calculation that involves a combination of those two that tells us something that neither individually would have. So if I were to be betting on this today, and again, being on the record about this, I'd say that there'd probably be advances in thinking about strongly correlated condensed matter, thinking about spin liquids that would come from the intersection of what you can do on the largest classical systems out there, as well as these quantum systems that'll get us there in the next couple of years.
So the next couple of years is 24, 23, 25.
That's plenty of time. I think anywhere between 23 and 25 is a good bet.
Thank you. Nathan, I'll go in reverse order. So you're next.
Sure. So my take on the matter is, when quantum computing ends up becoming useful, to some extent, is an element of subjectivity to it, because, for example, I think that the first applications realistically are going to be actually that are scientifically interesting are going to be simulations of toy models. Most likely, I think the first ones that are going to be done will be examples of simulations of toy models like the Hubbard model, or systems like free electron gases. These things are amongst the easiest physical systems to simulate on quantum computers, and they also provide a lot of insight to the behavior of systems. Well, they're not quite the same thing as solving, like a particular battery problem for Daimler or some other application like that. They nonetheless will be scientifically interesting, if not commercially useful. But on the other hand, the thing is that, what we'd be looking at most likely in the near term for this would be potentially signs coming back from noisy devices of effects that seem interesting or perhaps evocative for other people. But it's worth bearing in mind that, if we take a look at that existing gate error rates that we end up having for quantum computers, a good gate error rate, let's take a look at the claims that Google have ended up making as a point of comparison from the Sycamore chip. You've got about 0.3% gate error rates for their 2-qubit gates, much higher for measurement, but that's what they're claiming. So if we take a look at that, realistically, we can, best case scenario, end up doing algorithms that are on the order of a couple hundred gates, best case scenario. If we take a look at the gate counts that myself as well as my collaborators have done, we believe that the first applications that we could do that would be have small errors that would allow it to be quantitatively interesting would involve about 100 million to a billion gates. And at that point, what we're really looking at is we're looking at quantum error correction. Until we end up getting a clear runway, knowing how long it's going, or how effective existing quantum error correction strategies are going to be, I'd really hesitate in order to be able to make a good guess about when, for sure, quantum technologies are going to be useful, even for these more compelling applications, let alone less compelling, controversially speaking, applications in finance and optimization. So I would say that, I wouldn't be surprised if people are doing quantum experiments that physicists find interesting within the next 5 years. I don't believe that we're going to be doing anything based on what I've seen that will be useful for at least 10 years, but we'll only know for sure when quantum error correction is validated.
Chris, your take on this question.
Yeah, thanks. And I think differentiating myself from the rest of this group, I used to be a scientist. Now I'm in business development, so I'm going to take that perspective on it. And at Zapata, we've been doing some work recently that we're going to publish here in the next couple of months on variational quantum eigensolver. And there's a measurement challenge that goes along with that algorithm. And so we've done some work to deal with that problem, and you'll see it shortly. But as a consequence of that work, we did an estimate on when we would have enough resources to go after, some problems that we happen to be doing today with a large petroleum company that we'll probably talk about at the same time. And the conclusion really was, 2023, 2025, before we could start, really tackling some problems of real interest to that company. And also concluded that you have to have the error correction. So I'd definitely be in agreement with Nathan, but I'm going to take a more optimistic spin on it. The industry is moving fast. There are lots of challenges left to tackle, but I've been a little surprised at how fast things are changing.
Thank you, Chris. So we're settling on 23 to 25. So Martin, do you disagree, or do you have, let's hear what your point of view is.
Yeah, I mean, a lot of good points were already made. Let me point out let me give you kind of three different answers to your question. So I'm trying to tease it apart a little bit. I think in terms of business impact, we're already feeling it today. You can have business impact today based on quantum computing. We have a rich startup community. Chris is a representative of that. Those companies are delivering value today to their customers. There is a quantum-inspired optimization. Those are like completely classical methods that boost optimization problems. They're quantum mechanical in thinking, but you can run them today on classical hardware. And those solutions arguably would not have been discovered if it hadn't been for quantum computing and quantum information.
Highly arguable.
Right. So thirdly, in terms of the impact, so think about, for instance, what NIST has done, right? NIST has made a new call for crypto systems, for coming up with new crypto systems to replace existing cryptographic technology. What a revolution, right? Nobody wants to do that, obviously, but it's happening, and we're in the middle of that process. Quantum computing has already influenced that to a great degree, and it's a shift in the entire industry that happened because of quantum computing. So these business impacts are there. The scientific revolution arguably has already happened, right? Talking about timelines, with the showing that there are sampling problems that can be done on a quantum computer, but that you cannot do on a classical machine. That completely kind of falsifies the strong church Turing thesis many people believed in for a long time, that you could map any computational process to a computer, right? So it's a kind of those revolutions happen. But of course, your question hints at the commercial valuable applications, and there I'm entirely with Chris and Prineha and Nathan, that chemistry and material science will be very likely the first commercial valuable applications. And of course, there to really tackle interesting problems, you need to have some transition metals in them. Otherwise, classical methods can do a pretty good job predicting, say, energies or reaction rates. So that will only happen when we have a fault-tolerant quantum computer, and it's everybody's guess when that will be. We've seen some really amazing progress towards quantum systems that have the ability of measurement, feedback, and then corrections. There are several groups who have done that in ion traps and also in superconducting qubits. And I think we're just at the beginning of that. It's hard to predict how fast it will go. There have been so many roadmaps already from DARPA, ARDA. Europeans have their roadmaps. It's hard to put a time on it, but this seems to be happening for sure.
Thank you, Martin. So I think some of you answered my next question. So I'll put the question out there and then summarize what I think I heard from you. But if you disagree, then say so. So my question was, what will be the most significant breakthrough in quantum computing architectures in the next 5 years, and why? And it can't be just scaling to higher qubit counts. That's not a useful metric. And so I heard from all of you that fault tolerance and error correction are the important barriers that you would like to be seen resolved, and are the barriers on the way to useful quantum computing systems and applications. So I see some of you nodding, and if you disagree, you can speak up, or if you have an alternative challenge that you want to throw out and say, yes, but also this needs to be addressed. What are the most significant breakthroughs that need to happen in the next 5 years?
Let's just say I'll add to that and say, you know, of course, we
Okay.
understand what we need for fault tolerance and working towards something that is truly scalable. But something that gets a little bit overlooked, of course, is that you'd want to be able to connect these quantum computers. And in order to do that, I'm sure there's a you know, different part of this workshop that's going to talk about quantum networks. And one of the best ways to do something that allows you to connect various quantum computers is to have some way to network them. We know this was really important for classical systems as well. The simplest case of this could be, you know, you have two traps and you want to be able to connect across them. There are algorithmic questions associated with what would that mean for a problem you're trying to either distribute or discretize over, say, two traps versus something that is on a monolith, or if you wanted to do something equivalently across heterogeneous hardware. So I think approaches that somehow blend the network as well as the quantum computing side of things will be breakthroughs that are already, I think, being planned and will be made. And I think that they will increase the power of smaller quantum computers more so that we might be able to appreciate today.
And so since you're representing small companies in startup mode and large companies, but also in part the academic community, from your perspective, what would you like the QIS centers to do, or what else could DOE to help you to advance the state of the art in quantum computing?
You know, I was thinking about that question this morning, and you know, as somebody who used to be an experimental scientist, I think you know, what the DOE has done is definitely a good visionary step forward, and the way I kind of found myself framing it this morning is, you know, quantum computing, whether it's 5 years or 10 years, depending upon which argument you favor. I'm on the 5-year side, less than 5 years, but you know, this is the potential of quantum computing is in some ways existential for economic impact on the United States. It's also existential for national security impact on the United States. And so each country is going to have to pursue this for those two reasons, no matter what. And so, you know, how as the DOE being part of the United States, a government institution, how are we going to go fast enough to make sure we compete? And a great way to do that is to treat it like the space program back in the 60s, and to be sure that you know, we're not letting process get in our way. And the way I came up with thinking about it is, you know, one of our investors is BASF, and they're a chemical company. I'm a chemist, so of course I think about chemistry problems. And you know, I call up BASF and I say, hey, let's do a project together, and we agree on something we'd like to do, and we write a proposal, and then, you know, maybe BASF funds it, maybe we don't fund it at all, and we do it with internal research dollars. Better yet is that we have a mechanism in the US where, you know, these 5 centers make it easy for us to go and get access to hardware, and not just the hardware, but also the plethora of software tools that are available, so that, you know, BASF can explore quantum computing and how it can impact their business, and how Zapata, part of this ecosystem we live in today, can survive. And I think it'd be good for the country, it'd be good for the industry.
Thank you, Chris. And so I'll use the opportunity to make a plug for the Advanced Quantum Test Bed, AQT, at Berkeley that DOE is funding. And there was a call for proposals out, and we actually received some more than 20 applications.
Wow.
To do exactly what you just said. This is not just access to hardware, but access to the whole research team and exploring questions that you'd like to explore.
I'm biased in saying this. I'm part of one of the NQI centers that is led out of Oak Ridge, and I see an absolutely unique opportunity to do co-design. Okay, and this is where you really, and this is to a theorist and somebody who really has stayed very far away from you know, any kind of hardware their whole life is a dream come true, that you know what's coming, and you can also talk with somebody that day that might be able to make a change that either validates or invalidates a hypothesis I have. I think that cycle being on the order of hours rather than on the order of weeks or months from when I put something on the archive and somebody goes and measures it and tells me something is incredibly powerful associated with these centers. And I think that I second everything that was said regarding access. I think having access to the teams and knowing more about their hardware capabilities in real time could be useful. But I also think that the pairing there to do true co-design is going to be important in order to hit this crazy timeline that I put forward in the previous question. So,
okay, thank you, Prineha. So, Martin or Nathan, any words?
One very important functions the centers have, in my opinion, is the workforce development in the United States, Canada specifically. Yes. It's clear that we need more positions in that field. Kind of, there are not enough jobs, there are not enough sustainable jobs, so you can build an entire career on it. But also what's still lacking is like the educational aspects. How do you actually get a degree in quantum information or quantum computing? Some universities offer it, but there's a great opportunity to do that across the field. It's a great opportunity for companies to offer certifications in certain disciplines, right? So you maybe that will go onto your resume one day that you're certified as a programmer in that area. And the centers can play a very important role because there will be movement between the centers on the postdoc level. There will be long-term efforts at the centers, and they can sort of work as an amplifier for the workforce. And of course, then industries tremendously benefit from having that workforce and can immediately hire people from the workforce or as interns or as permanent staff. So I think that's a very important function of the centers. That's great.
Nathan, last word.
What I would say first and foremost is invest in junior people, period. Because a major challenge that I end up seeing, especially inside the DOE run labs, is that the DOE ends up often getting people who are junior jumping from one project to the other based on when funding can end up showing up. And you have a ton of people who have epsilon exposure to a zillion different areas. And if internally the DOE wants to build up its strength in QIS, it needs to have a long runway. It needs to give people guaranteed funding, and it needs to provide ways for people to prosper and become experts in this complicated field.
Thank you, thank you. This is a challenge for everybody in the labs, unfortunately, not just for early career scientists. Okay, well, thank you for your opinions and thank you for a lively discussion.